Hello, my name's Peter Gainsford. I'm a classical scholar based in New Zealand, and today I'm going to walk you through a short 2-minute video made by IBM in 1961 about Eratosthenes' measurement of the Earth. We're going to do a fact check, a review of what's correct and what's not correct in this video. The reason I'm doing this is because most popular accounts of, in fact pretty much all popular accounts of Eratosthenes' measurement of the Earth that you will find out there are absolutely packed with false claims and mistakes. Let's see how this one does. I'll be stopping and starting. Here we go.
How would you set about to measure the Earth with the mathematical knowledge and tools you already possess? A Greek named Eratosthenes did it 240 years before Christ.
All good
He
so far?
was head of the great library of Alexandria in Egypt,
Also
a city
correct.
built by the Greeks. He, like others, suspected that the world was round. After all, the sun and the moon were round.
Okay, this is false. He did not suspect that the Earth was round. He knew perfectly well that the Earth was round. This was common knowledge. The discovery of the shape of the Earth was about 150 years before his time. So this is not something newfangled that we're talking about. This is like, think about what science was like 150 years ago from today. People were just starting to discover things like radiation and so forth. This was a well-established discovery by Eratosthenes' time. One of the things that videos like this and other popular accounts get wrong is that they underestimate the importance of the book culture that was prevalent at the time. Not many books from this period survive today, and it's easy to make the mistake of thinking that there weren't many books. There were thousands. There were hundreds of thousands. As we'll see. Now, how do we know that the Earth was known to be round by his time? Well, a couple of generations before Eratosthenes, we find Aristotle talking about empirical evidence for the shape of the Earth in his treatise On the Sky. And a few decades before that, we find Plato in his dialogue with Timaeus taking the Earth's shape for granted. Now, we know it wasn't long before Plato that the Earth's shape was discovered. Basically, we don't have an exact record of who it was that made the discovery or exactly what reasoning they used. That's a discussion for another day. But we do know that prior to 400 BCE, everyone that talks about the shape of the Earth, and there are quite a lot of philosophers, pre-Socratic philosophers, talking about the shape of the Earth prior to 400 BCE, and they are absolutely unanimous that it's flat, or approximately flat, with some variations. So before 400 BC, absolutely everyone was a flat earther in Greece. After 400 BCE, it's basically difficult to find anyone who was still a flat earther. Maybe Epicurus, but not many others. So there is a very sharp... like I said, Plato takes this for granted. He takes the spherical Earth absolutely for granted, and we have already in Aristotle round about maybe 220 BCE, 320 BCE, talking about the evidence for the shape of the Earth and even estimates for its size. So Eratosthenes wasn't the first person to talk about the size of the Earth either. He was the first person to use empirical evidence to measure it. When Aristotle talks about the size of the Earth, he gets the figure wildly wrong, quite wrong, and it's pretty clear that it's just an estimate. Archimedes also has an estimate for the size of the Earth, although that's roughly contemporary with Eratosthenes, probably a bit earlier because Eratosthenes got a better measurement. So let's carry on.
He had also noticed that the sun's rays fell in parallel lines.
Approximately.
Greeks before him had divided the circle into degrees and had measured angles.
This is false, or at least it gives a false impression. The division of a circle into 360 degrees was a development in Babylonian mathematics, so centuries earlier.
With this information and a logical mind, he measured the Earth. Here is how. While visiting the city of Syene one midsummer's day,
False.
Eratosthenes noticed that the reflection of the sun could be seen in the bottom of a deep well.
False.
The sun was overhead, and the rays pointed to the center of the Earth.
We better stop there. No well. Actually, that's a kind of confusing image still to stop on.
He remembered.
Okay, so multiple falsehoods here. First, no well was involved in the story of Eratosthenes' discovery of the Earth's shape. A well was built in Syene to demonstrate the fact that Syene lay on the tropic, and so that there were no shadows at the summer solstice. But this appears to be later than Eratosthenes' measurement, so nothing was based on a well. Now, how do we know this? We don't have Eratosthenes' original writings. What we do have is fragments. And these fragments, the relevant fragments, are collected very helpfully in Dwayne Roller's edition of Eratosthenes' Geography. Now, the Geography was essentially a treatise on the science of geography and cartography, and probably some information relating to Eratosthenes' atlas of the known world at the time. But at the end of this book, Roller very helpfully gives an appendix with fragments relating to what Eratosthenes wrote about the measurement of the Earth. And it's only a few pages. You can see it's just 9 fragments strewn across 5 pages of a modern edition in translation. If you look at one of these fragments in detail, or any of these fragments, you will not see any reference to a well. A well is described by Pliny the Elder and Strabo, both writing in the 1st century CE. One of them, I think it's Pliny, is explicit that the well was built specifically to demonstrate the fact that Syene lies on the tropic, and therefore you have no shadows at the solstice. We'll come back to this, and let's carry on with the video for a bit.
And on the next midsummer's day in Alexandria...
I have to stop here and point out that the calendar on the wall here is obviously a bit of a joke. Eratosthenes did not know that he was living before Christ, BC, and the 21st of June is a date in the Roman calendar, not the Egyptian calendar that Eratosthenes was using. The two calendars are quite different. It's just a bit of a joke.
He measured the shadow cast by an obelisk.
False.
Sunbeams travel in parallel lines.
We'll come back to that.
The difference in angle had to result from the curvature of the Earth. If the angle was 1/50th of a circle, then the distance around the world must be 50 times the distance from Alexandria to Syene.
Okay. Parts of this are accurate. If you look again at the fragments that we have of Eratosthenes' measurement of the Earth, you will see that they do describe something like this procedure. For example, here Cleomedes, fragment 6 here, is the most detailed account that we have of Eratosthenes' measurement. You will not see any mention of obelisks. What we do have is references to the use of gnomons, which is that is to say, the spiky thing that sticks up vertically in a sundial. But you can also use them without a sundial to do things like measuring. There are several things that you can measure using a gnomon. When the shadow is at its shortest, you know that's midday. That's the transit of the sun, and that's the sun is on the meridian. The day of the year when the shadow is at its shortest if you're north of the tropic, is the summer solstice. When it's longest, that's the winter solstice. When the shadow is at its shortest in the middle of the day, you can also tell that that's the direction of the shadow is due north. So these are all things that you can measure with a gnomon without having the sundial around the base. Now, what we have here in Cleomedes, the actual ancient text that Eratosthenes' method is known from, what we have is a description. On the left-hand page here, you've got when the sun makes the summer solstice, exactly at this meridian, by necessity, the gnomons on the sundials are shadowless at Syene, because it's on the tropic, since the sun lies exactly above. This is said to be an area 300 stadia in diameter. A stadion is an ancient Greek unit, roughly 177 to 191 meters, customary for converting to modern units. It's pretty customary to use a rate of 185 meters to the stadion. So 300 stadia would be, I can't figure that out in my head. It's away, about 30 kilometers or so, I guess. Less. Okay, so let's carry on. In Alexandria, however, at the same time, the gnomons on the sundials cast a shadow, since the city lies further north than Syene. Okay, fine. So then we have a description of more of the details. And on the right-hand page, you've got the arc drawn from the point of the shadow of the gnomon around to its base, stands on this and that from Syene to Alexandria. Yeah, this gets pretty technical. We do get to the key bit at the end of the paragraph. The one in the basin is found to be a 50th part of its own circle. Necessarily, then, the distance from Syene to Alexandria must be a 50th part of the great circle of the earth, and this is 5,000 stadia. Thus, the entire circle is 250,000. This is Eratosthenes' procedure. So, like I said, that's the most detailed account that we have of Eratosthenes' method. Now, it's pretty obscure what he's talking about there, but if you draw a diagram, you do get something pretty much equivalent to what we saw in the video. We start off with the assumption that the sun is distant enough that its rays are parallel. At the summer solstice, at E, Syene, the sun's rays are coming from directly overhead, and so the line from the center of the Earth to Syene is continuous with the line of the sun's rays. Meanwhile, at Alexandria, point A, you're going to have a shadow. Now, what Cleomedes describes is that since the lines to F and F' are parallel, therefore the angles CBD, from the center of the Earth to the gnomon at Alexandria, and the angle BCE, that is to say, with the angle between the two gnomons and the center of the Earth, those are equivalent angles. Therefore, the arc AD and AE are similar. That is to say, they occupy the same proportion of a circle. Therefore, multiply the arc AE, the distance from Syene to Alexandria, by 360 degrees divided by angle ABD, and you get the circumference of the Earth. Feel free to go back. Hang on, I'll bring this up again so you can actually go through this text yourself. Feel free to pause the video and look through and check that it's what I've described. So that that is what Cleomedes describes, and that is the fundamental geometrical principle underlying Eratosthenes' measurement. There are reasons to have reservations about this. What Cleomedes and below him Martianus Capella describe is that Eratosthenes was using excuse me, here's how Martianus Capella describes it further down the page. A gnomon, these are round containers of bronze called scaphia, which mark the course of the hours by means of a vertical stylus placed in the center. So you've got a bowl with markings, gauge markings along the sides, and a vertical stylus in the center, with the gnomon. The problem is precision. If you think about how precise the ratio of the shadow to the gnomon would have to be to produce a measurement of 250,000 stadia, or 7.2 degrees would be the angle, you would need a really very high degree of precision. Take a look at this table here, where I've drawn up the kind of precision, the kind of errors that you get if you have an imprecise shadow measurement. If the ratio of the shadow to the gnomon lies in the range 0.12 to 0.13, you end up with a range in the circumference of the Earth ranging from 240,000 stadia to 260,000. Now, Eratosthenes purportedly comes up with a measurement 250,000, or in some sources 252,000. And this is very close to 7.2 degrees. Cleomedes is quite explicit, though, that it is precisely 1/50th of a circle. That's what Cleomedes says. I have seen an article recently arguing that the variation between 250,000 and 252,000 is a consequence of varying measurements in other respects, but Cleomedes is quite specific. 1/50th of a circle. How do you get 1/50th of a circle from measuring a gnomon and its shadow and taking the proportion? Well, take a look at this table and you'll see, I'll tell you right now that you need to have measurements of the gnomon and the shadow that are precise to 3 significant figures to get a circumference of the Earth that is accurate to 2 significant figures. I think we have to take it that Eratosthenes' measurement of the Earth is precise to 2 significant figures, at least. Perhaps closer to 3 significant figures. That would mean that the measurements of the gnomon and the shadow would have to be precise to 3 or 4 significant figures. And while that's pretty straightforward using modern equipment, it's not so easy in Ptolemaic Egypt. We have ranges for the measurement of the Roman mile, which are barely accurate to 3 significant figures. The Romans could get 3 significant figure precision. But the stadion is barely accurate to 2 significant figures. How precise were the gnomon and the shadow as measured by Eratosthenes or his predecessors? That is an open question, and I have my doubts that the measurement is precise enough. I think that this is the geometrical basis for the reasoning, but I suspect that it's quite possible that the tools that Eratosthenes actually used for the measurement, or the tools that other people he relied on used, were quite different. Because think about how many levels of error you're going to have in a measurement like this. You've got error in the measurement of the gnomon, both gnomons, because you're using 2 gnomons at 2 different places, right? You're going to have 2 errors in the measurements of the shadows. So you've got 4 errors there. Let's assume that the ratio calculation is precise. Oh, actually, if you're measuring at the summer solstice, there's no shadow measurement at Cyane, so you've got 3 errors there. And then you've got the error from calculating the angle. How do you get from a shadow-gnomon ratio to an angle? How would you do it? I would do it by taking a calculator, plugging in the ratio, and using the inverse tan function. Eratosthenes did not have a calculator, and he did not have trigonometric functions. Some ancient mathematicians do draw up chord tables, which are a kind of proto-trigonometry, but nothing like the precision that you've got in this table. Nothing remotely approaching that precision. So basically, I don't think that the shadow-gnomon ratio is actually a realistic way of getting these angle measurements. What I suspect is that a device described by Ptolemy is a much better candidate. This is in Ptolemy's Almagest. The basic idea is that you have this device represented on the right-hand page here. This is in Book 1 of the Almagest, Chapter 12. It's two concentric rings. The inner ring, and you can move the inner ring around. It's on a rail, so it can rotate freely. You have two ridges on the inner ring, and at midday you have this device lined up along the meridian. At midday, so it's exactly so the shadow is exactly in line with the device, and at midday you arrange the inner ring so that the top ridge is casting its shadow on the bottom ridge. Then you read off an angle measurement on the outer ring. And doing this, you are not having to worry about imprecisions with the length of the gnomon, imprecisions in the measurement of the shadow, and imprecisions in calculating trigonometric functions in a time before trigonometric functions existed. You are directly measuring angles. Now, this is in Ptolemy. This is in the 2nd century CE, so 400 years later than Eratosthenes. However, and on the left here you can see a diagram with the ridges shown. A casts its shadow on B at midday. We do have a graffito from Meroe, which is also on the same meridian. It's in modern Sudan. It's the old capital of the Kushite Empire. And in Hellenistic times, in the 2nd century BCE, so only a few decades after Eratosthenes' time, we find a graffito there which seems to illustrate someone using one of these devices to measure the sun's angle. And the graffito on the right here, you can see, shows someone sitting in front of what appears to be a circular device, and at the top left you've got the sun's rays shining down and hitting the device, and you're reading off needle measurements on the gnomon. So this is, like I say, this is just a few decades after Eratosthenes' time, and this would be a way of directly measuring the angles without having to faff around with trigonometry, precise measurements of yardsticks, gnomons, and shadows, and imprecise trigonometric calculations. I think this is a much more realistic way of doing it. The only evidence that we have going for this, however, is this graffito at Meroe and Ptolemy's description of the device. So, I mean, this model is not going away, but there are better ways of doing it, and there is a much better and perfectly realistic way of doing it that we find in Ptolemy and in that graffito from Meroe. So anyway, that's my proposed candidate. I think this is a better candidate for Eratosthenes' measuring device. Now, enough of a pause. Let's finish this video.
With these simple tools, Eratosthenes made this almost exact measurement of the world.
What units are those? So 1/50th of a circle, right, times 500. I'm pretty sure that they must be thinking of miles, modern imperial miles. Eratosthenes did not use modern imperial miles, he used stadia. And like I said earlier, the conversion rate between stadia and modern units is quite imprecise. So this is absolutely wrong. Hang on, let me just work out what would 5,000 stadia be in modern miles? Well, actually, hang on. Let's work that out. Let's just use Google. 500 times 1, let's see, 5,000 times 0.185 will give us kilometers. Sorry, I typed it as plus instead of times. So 925 kilometers. And what's 925 kilometers in miles? 575 miles, so not 500. And, oops, what's that times 50, just for reference? So that would give a circumference of 28,700 miles. It's wrong. But anyway, let's finish.
More than 1,700 years before Magellan sailed around it. He was a friend of Archimedes.
There is no evidence whatsoever of that.
He was a mathematician and a poet.
True.
Invented the sieve for finding prime numbers. Was the first geographer.
Kind of. Yeah, actually, no. I think that's a fair claim. Actually, Eratosthenes basically invented the idea of lines of latitude and longitude. He was the first person to use that coordinate system for plotting maps. There is a story of, I think it's Anaximander, drawing a map, but no such map survives. And if he did draw any maps, they're not going to have been very accurate at all. We certainly don't have anything remotely approaching a modern map. Ptolemy's map in the 2nd century CE is moderately accurate for the bits of the world that he knew, that were nearby, that the Romans knew, but we have no information about how accurate Eratosthenes' map was. I mean, put it this way, he drew the Alexandria meridian going from south to north. His meridian goes through Meroe, Syene, Alexandria, Rhodes, Lysimachia, and Olbia, and that takes us up to the south coast of Ukraine. So Ukraine down to Sudan. The actual range of those places aren't actually on the same latitude. There's a range of something like 7 degrees. I mean, it's not too bad, but measuring longitude is hard, and it wasn't really solved until the modern era.
And corrected the calendar to the one we use today.
Absolutely outright false. We don't have anything indicating anything of the kind. That's completely made up. The calendar used in Ptolemaic Egypt was nothing like the modern calendar. I mean, it had 365 days in the year, but I mean that's the only point of and it had 12 months because there are 12 moons each year. But I mean, the calendar was 12 months of exactly 30 days each, and then 5 extra days at the end. I mean, that is not the calendar that we use. The calendar we use is the Roman calendar, as modified by Julius Caesar, and then modified again in the 1500s. So that's a totally fabricated statement. And that's the end. Okay, so so that video has many elements of accuracy about it, but if you actually go and read the ancient sources, as I suggested that if you really want to get to grips with this, you can't just rely on what popular accounts are saying. I started with this IBM video because it's short. I've actually gone on for ages, haven't I? But there are loads of inaccuracies in there and loads of grounds for doubt, reservations. There is a lot that you can't find out unless you're actually looking at the ancient sources. And there's not too many to look at. It's 5 pages. If you want to have an accurate account of Eratosthenes' measurement, you need to look at these 5 pages because they are the evidence. Don't just repeat nonsense about a well which is not borne out by any actual evidence. Not to mention obelisks. There was no measurement of obelisks. Read the sources. They're not hard to get. They are sometimes hard to interpret, but that's why Roller has produced this edition with a very nice introduction. Okay, admittedly, this came out 50 years after the IBM video. But there is still a tendency in the present day for people to ignore the actual evidence when giving accounts of things like this in antiquity. And that is why I have written up a much more detailed account on my own website, Kiwi Hellenist, and you can go and read it here. It's a 4-part series on how Eratosthenes measured the Earth. I think I may have been a bit too firm in my support of the idea of using that circular device described by Ptolemy, although I do still think that it's by far the more likely candidate for the measurement equipment that he used. But other than that, you will get a reasonably accurate account here that is actually grounded in ancient evidence. So, don't trust what you see in popular videos. Go to the sources. I took on this IBM video because it's short, just a 2-minute video, as a kind of preparation for tackling the most influential account of this accomplishment, which is a much more influential account is to be found in Carl Sagan's Cosmos, episode 1, which came out in 1980. Practically all modern accounts of Eratosthenes' measurement are based on Carl Sagan, and literally only 50% of what he says is true. And the reason for that is because he doesn't look at the actual evidence. He relies on, you've got modern accounts relying on what Carl Sagan wrote and said. You've got Carl Sagan relying on half-remembered stories from when he did his degree in the 1950s, and it's all half-remembered, half-baked fabrications going all the way back. If you actually look at the evidence, you will find out what we actually know about this story, and it does not involve wells, it does not involve obelisks. It may have involved gnomons. I have my doubts about that. And it did not involve a distance of 500 miles or 800 kilometers between two cities. There are further areas of uncertainty as well. I think there's good reason to question whether the measurements were actually taken at the solstice. Most latitude measurements that we find in ancient sources rely on measurements of the sun's angle taken at the equinoxes, not at the solstice. And there's also a question over which places he was using measurements from. Alexandria and Syene, sure, those are talked about in some sources, but we also have Meroe talked about in some sources. And Eratosthenes thought that those three cities were equidistant. They were all 5,000 stadia apart, going north to south. Alexandria, Syene, Meroe. There's a lot of uncertainty here. If you want an accurate account, basically don't trust popular sources at all. I wouldn't trust them an inch. Should you trust me? Maybe, maybe not. But if you want to actually look at the evidence yourself, I've given you the tools to do so. You just have to go and find Roller's edition. Thanks for listening, and I'll hopefully be coming back to you in the future with some more fact checks along these lines. Bye for now, and thanks for listening and watching.